Welcome everybody to the second part of JUICE and observations of the interstellar 3I Atlas comet. We have three speakers for you today. I will introduce in a bit. We have a very short update about the status of the JUICE mission by Claire Vallat, who is with the JUICE project, and she is at ESAC.
It's going to be a very short update because I expect that some of you were already there during the last the part one of the 3I Atlas webinar 2 months ago. Quick status: so we are on our way to Jupiter. We will arrive in 2031. As you can see here, you have a summary plot of the cruise phase of JUICE. We have the time in the x-axis and the distance to the sun in orange and to the Earth in blue. And the background indicates when we are close or very close to the sun, where we have thermal constraint applying. So as you can see, we are for the first time in what we call the cold cruise. We are doing our first excursion, but we are heading back to Earth in 3 months from now. Sorry. So we will fly over the Earth at the end of September. But before this, and as you know, and as it will be the topic of today, we had the chance to be very well placed to observe Atlas while it was going through the solar system and closer to its perihelion. One quick word about the Earth flyby. So that's the third gravity assist that we will have. We will have 4 gravity assists in total. So we had the first lunar Earth gravity assist in 2024, and we had last year a Venus gravity assist. So the next one is in 3 months from now. We will fly over Earth at roughly 9,000 kilometer altitude. We will arrive from the night side. And we will spend some time in the magnetotail of the Earth. We will take advantage of this gravity assist to perform a lot of essential calibrations from the instrument for all the instrument of JUICE. Actually, we will perform Earth and Moon observation in different wavelengths. Also, while JUICE will be in eclipse, where we have also some stringent constraints. And the in-situ instrument will also sample the plasma environment around the Earth. So yeah, we'll keep everyone posted, of course, and you will hear from us again very soon about this gravity assist. So yeah, so I will stop here and we'll leave the floor for the very interesting 3I Atlas results from the different remote sensing instrument.
So our first presentation will be by Paul Hartogh. Paul is a planetary scientist at the Max Planck Institute in Göttingen, and he's the PI for the SWI. So Paul, the floor is yours.
Thank you. So I'm going to talk about spectroscopic observation of 3I Atlas with SWI. So SWI is the submillimeter wave instrument. That means it's an instrument that performs spectroscopy in the range of wavelengths below 1 millimeter. In fact, we have 2 bands with the longest wavelengths of 0.57 and then another band 0.24 millimeters, or 570 and 240 micrometers, which is also called far infrared range. Frequencies is basically the lowest frequency 530 and the highest 1275 gigahertz, and here you see some 2 sketches of the electromagnetic spectrum. So we are somewhere here a little bit shorter wavelengths than microwaves, or in another plot you see here the submillimeter wave range, which is here shown between 1 millimeter and 0.1 millimeter, which according to this plot already belongs to the infrared. Therefore, it's also called far infrared range. So far infrared range means we are if you calculate the Planck function, you can see that we are sensitive to very low temperatures. That means even temperatures below 10 Kelvin. And that means also to very cold gases, but of course also solid state bodies. Another important point here of the principle of this submillimeter wave instrument is that it's a so-called superheterodyne or heterodyne spectrometer. And that is shown here. Heterodyne spectrometer means that you basically shift the received frequency range to, which is in the range of terahertz, thousands of gigahertz, to a frequency range where electronic processing can take place. So that is done here by a local oscillator. That is maybe a sinusoidal signal, let's say 1200 gigahertz. The signal we receive from the atmosphere may be 1210. So that the 2210 is shifted to 10 gigahertz, which is called intermediate frequency, where we apply the so-called real-time spectrometer. And that's the advantage of the method. You can use any spectrometer with any arbitrary spectral resolution. We have chosen so-called trip transform spectrometers, CTS, with a resolution of 100 kilohertz. So for above terahertz, that corresponds to a resolution of higher than 10 to the 7. And that means we can fully resolve line shapes. And quite often these line shapes contain information about the gas we observe. So, for instance, the number of molecules along the line of sight, temperature along the line of sight of the atmospheres, but also the resolution is high enough to measure Doppler shifts, for instance, caused by winds. And here are some examples for this kind of heterodyne spectrometers. On the upper left, you see a water vapor observed from the ground to space. And now the water vapor line has different spectral features depending on which altitude you are looking at. For instance, if you look at 80-kilometer altitude, horizontally, you would see a very narrow line. And if you go to 70, it gets wider, and so on. And for instance, at 40, it's already orders of magnitude wider than at 80. And if you observe from the ground, this adds all together to a line shape like this. And here you see a measurement of this water line from the ground. And in principle, you can develop now a model, a radiative transfer model, that models what you see on the left plot. And so in this case, you see a measurement, which is a noisy blue line, and the green line here is the model. It fits quite well. Here you see the residual, the difference between the measurement and the model. And the fit parameter in this case here is, so we assume we know the temperature profile, or we get the temperature from somewhere else, more or less a number of molecules per height. So it's here something between 0 and 8 parts per million. And in principle, you can then every few hours or so, if you measure long enough, the lines may be weak or strong. In this case, you have to measure a couple of hours. You get such a vertical profile, and it works day and night, in principle also during rain and so all weather conditions. And you can add up this kind of spectra in a contour plot. And in this case, you see a data set of about 2 years. And you see the annual variation of water vapor here at polar latitudes. And you see it's very high in summer and maybe very low in winter. So it's a very strong annual variation. Or here we see a plot from our colleagues, SWI colleagues from the Institute of Applied Physics in Bern in Switzerland, where people observed the ozone line on 142 gigahertz. And from the Doppler shift of the ozone line here over the time, they got this contour plot here and this contour plot here, and they compared it with the European Center for Medium-Term Weather Forecast, ECMWF in Reading. Reading is basically running a model of the middle atmosphere's temperatures and winds and composition. And they have a lot of data from satellites. They perform data assimilation, and you see that the very high similarity of this wind measurement from ground compared to the ECMWF model data for this location. But here we speak about a comet, of course, and there the line looks quite different, and also we don't have a pressure broadening. We have different parameters that describe the line shape. And again, here we observe this very high resolution, and with the two receivers, basically two lines, which are the rotational and ground state of water vapor. And these lines have a very large absorption cross-section. That means even for relatively low abundances, we can detect these lines. The one line is auto water, the other para water, so they have a different electronic spin state in the hydrogen, and the frequency is almost twice as high, 557 para, twice as high, 1113 gigahertz. And we observe this then with a nominal frequency resolution of 100 kilohertz, as I mentioned before. So here are some technical things which are important, written on the right side. For instance, we need a very good frequency calibration because we measure Doppler shifts here of these lines. Obviously, the gases from the comets, they move, and so we want to measure their speed as accurate as possible. Therefore, we have to be sure that our reference frequency is very stable, and we have therefore an ultra-stable oscillator, which on the other hand is locked and bound to a oscillator of the spacecraft, USO of the spacecraft, which on the other hand is calibrated against the ground station where they have atomic frequency standards. So we have a very high frequency accuracy here. And it's also important that we switch on the instrument early enough that it's stable. And that was all done here for this measurement, which happened between November 2 and November 6, 4 measurements of 25 minutes from an average distance of 64 million kilometers. And here's something about the geometry. On the right side, you see the sun. And here you see the spacecraft basically moving from 1st of November to 6th of November. And here you see the comet moving. And if you imagine, you observe basically from here, so 6th of November in this direction, you can easily imagine that you can see gas which is moving into this direction towards the spacecraft, but also gas which is moving away from the spacecraft. And that is important, and we will see that later. So for the data analysis, a few words. So we have this, I mentioned already, this highly resolved lines which carry information about the distribution of molecular density, velocity profiles, and also the total number of molecules we see in this coma of the comet. For the model, we need, so it's a radiative transfer model, we need inputs on the kinetical temperature, the number of electron temperature, but also the auto-to-para ratio, so the different spin states, remember. And also it depends on spectroscopic and collision rates, which have to be taken into account and assumed. Then the geometry, the beam size and efficiency, all this has to be taken into account. And so we proceeded with two different non-LTE radiative transfer models, one of Nicola Biva, the other of Ladi Rezak. We started with 1D spherical geometry Hazer model geometry, but it turned out that we cannot fit the line shape. So instead, we assumed basically two different comata, subsolar and antisolar. And that at the end led to a rather good fit of the spectra. So here's an example of Nicola. So here he indicates that he assumed subsolar, antisolar with different production rates and different outgassing speeds. And the result is that the production rate of the comet is something like 9 to the 28 plus minus 20% molecules per second, which corresponds to roughly, I think 3 tons or 2.7 tons per second. And as I mentioned before, to really get these features of the lines, we measured the 600, 1200 gigahertz range. We have to assume the subsolar, antisolar flow. And this is ongoing, basically. I think I would say 90% of the work is done, but we are still working on why is that, and why we have also a very strong, or let's say a stronger signal in the antisolar direction. And so the results are that we in the subsolar direction we have almost half as many molecules than in the antisolar direction. And the idea is that we have some kind of grains, ice grains, or ice particles on the antisolar direction, which after a certain distance starts to sublimate and maybe even are the main contributor to the coma. And anyway, so here in this case, in this model, we assume 3 and 6 times, ending up 9 times 10 to the 28 molecules per second. So the newest results are shown here, just from a meeting last Thursday. So the line areas here of the fits agree with the measurements within 10%. So there's still some improvement possible. Little refinements could be done, and we are working on that. And the latest results show antisolar 3.6 times 10 to the 28, and so subsolar and antisolar 6 times, so ending up is 9.6 times 10 to the 28, and the corresponding expansion velocities are 480 meters per second subsolar and 650 meters per second antisolar. And now I would like to talk about an application of this measurement. And recently, probably you have seen that there are 2 Nature papers published about the D over H in 3I Atlas, performed with ALMA and with James Webb. And amazingly high values of 40 times and 60 times Vienna standard mean ocean water. So the average D over H in water we have on Earth was found. Here you see the ALMA data. On the right side, the HDO measurements. On the left side, the H2O measurement. But you see the H2O measurement is extremely noisy. So that is basically what the authors indirectly derived for the H2O production rate. They could not directly measure it because it's too noisy. And and here we can come with SWI, where we have a relatively good signal-to-noise ratio observation. So interesting with the 3I Atlas is that here you see basically Earth, D over H in water, Enceladus, Oort cloud comets, and comets of the Jupiter family. Here you see D over H in hydrogen and the giant planets. That basically the values are all below 4 times Vienna standard mean ocean water in the solar system. And if you compare here with 3I Atlas, it even doesn't fit here into this plot. So it's really orders of magnitudes higher. And a larger picture is shown here, the D over H that has been determined in the universe. And we see the highest values are in envelope around young stellar objects. And the highest value here ever seen is something like 30 times. No, I can't see it here, unfortunately. I don't know where, but I think 32 times V small. And so we have seen D over H in an object which is higher than anything else observed, maybe except Venus, but that is another story. So if you now take the derived value of Salazar-Manzano, so the ALMA observations, which are 6 times 10 to the 29 molecules per second, and we replace this value by our value, we get even 70 times V small. That means more than 1% D over H ratio, and even higher than basically the value of James Webb. So that's it. 2 spares quickly. So some fundamental work on this deuterium enrichment was done by Alexander Thielens in his PhD thesis in 1982. And interestingly, also Wing Ip, basically based on Thielens' PhD thesis, he predicted that there may be comets which have 1% D over H ratio. And finally, it was found. Thank you for your attention.
The next talk will be by Dominique Bockelée. Dominique is an expert in cometary atmospheres. She has been studying especially their composition using radio infrared observations, both from the ground and from space. Of course, she was very much involved with Rosetta. She's a co-I of Juice SWI instrument and the MAJIS instrument. And today she presents observations from MAJIS. So Dominique, the floor is yours.
Okay, so hello everybody. So I will present you the observations of 3I Atlas with MAJIS on Juice. And the results are the object of a paper which have been submitted to APG letters. So MAJIS is a long slit spectrometer with 400 special elements along the slit, and with each spatial element having a spatial resolution of 35 arcseconds. MAJIS has 2 spectral channels, one covering 0.5 to 2.35 micron with a spectral sampling of 3.5 nanometer. And the other one, near channel, is covering 2.28 micron to 5 to 56 micron with a spectral sampling of about 6 nanometer, which correspond to the spectral resolution of 500, about at 3 micron. And MAJIS has a scanning mirror to make images, in fact, to get hyperspectral images. So the comet was observed with a low signal readout mode, which was just uploaded in the spectrograph. So this mode was used for the first time and allowed to get data with a much higher signal-to-noise ratio. And each observation consisted in a 23-line scan across the slit. And you see an example on the right of the an image which was obtained at spectral wavelength of water, and which is superimposed on the NavCam image of 3I Atlas. So we use this 23-line scan on four dates on November 2, November 12, November 19, and November 25. So the heliocentric distance was from 1.33 astronomical unit to 1.67 astronomical unit. So we have a good heliocentric coverage, and the distance of the spacecraft to the comet varied a lot from 0.4 astronomical unit to 1.3 astronomical units, which means that the spatial resolution varied from about 10,000 kilometers to 29,000 kilometers. And this means also that the signal decreased a lot with time due to this increased distance of the spacecraft to the comet. So this observation, this data provided first the detection of water and CO2. Water from is bound, vibrational bound at 2.7 micron, as you see on the left, top left, you see the spectrum of water detected on 2 November. And we detected also CO2 from its band at 4.27 micron. And for these two molecules, which were detected at all dates, we obtained maps and image. And so you see the image for all the dates for water in the top and CO2 on the bottom. So what we did first is that we fitted the band with a planetary spectrum generator developed by Geronimo Villanueva. And the fit, you see the fit in orange. So this fit shows first that these bands are due to reverberational fluorescence emission from this molecule. And from this fit, we were able to determine the excitation state of the molecule, in fact, by determining the rotational temperature, which was determined to be 46 K for water, for example, on November 2. In fact, what we verified is that this rotational temperature is quite in agreement with the model which is used for interpreting the SWI observations. That is a model which considers collision with electron and radiative pumping of the vibrational band. For CO2, we determine a larger temperature, which is 80 K in the case of 2 November, and this is expected, this larger temperature with respect to water, due to the fact that CO2 has no dipole moment, so cannot relax. The rotational level cannot be depopulated by spontaneous emission. So thanks to these maps, it was possible to study the radial distribution of the molecule. So you see on the left the radial distribution of water and on the right of CO2. And so it was possible to compare this radial distribution to models, and especially to the model assuming that water and CO2 are released from the nucleus. And so this model, this other model is shown in gray dashed line. And what you see is that the radial distribution of water and CO2 are consistent with the production of this molecule very close to the nucleus, or from the nucleus, of course. And the limit of production is 1,000 kilometers. This means that this does not exclude that water is produced from short-lived icy grains within 1,000 kilometers from the nucleus. For CO2, what we observe is that the radial distribution is somewhat a little more compact than expected from this other model, that is outflow at constant velocity. And this more compact distribution, in fact, can be consistent with gas acceleration. And we know that in the coma, the molecules are accelerated somewhat in the inner coma due to some heating, due to collision with quite rapid hydrogen. So then, of course, these observations are quite interesting because they provide the water and CO2 production rate near perihelion. So for water, there have been numerous indirect measurements of the water production rates, indirect measurement, but also direct measurement. I show here only some examples. For example, the detection of water with the James Webb telescope at 3 astronomical units from the sun, or the detection of OH radical at 18 centimeters with the Nancy radio telescope. Another key instrument which provided a water production rate is the SOS1, which measured the water production rate from the Lyman alpha emission from hydrogen. So for water, we have a lot, I would say, a lot of data. But for CO2 and also for CO, we don't have so much data. For CO2, first, because CO2 is not observable from the ground, from ground-based telescope. And so MAJIS is providing a key measurement, especially near perihelion, and measurement which is not available from other instrumentation. So here the production rate which were derived. Near perihelion on 2 November, we measure a production rate of 2 plus or minus 0.8 10 to 28 molecules per second for water. And this is quite in agreement with SWI data. And this production rate decreased as the comet recedes from the sun. And for CO2, we measured about 10 times less with respect to water. So what is interesting, you have in the right, the plot given in the right, you have in this plot production rates which were measured by different techniques. For water in blue, with empty symbol giving measurement pre-perihelion and solid symbol post-perihelion. So water in blue and CO2 in red and CO in green. So what is first interesting is we notice that the production rate measured by MAJIS is 3 to 4 times lower than the production rate measured by SOS1. And if these SOS1 measurements are correct, in fact, this indicates that, in fact, the molecules, the water molecules which are seen by MAJIS and also by SWI are not the same as the ones seen by SOS1. And in fact, SOS1 could be sensitive to molecules which were produced by long-lived icy grains. Indeed, the field of view of SO is much larger than MAJIS and SWI. So, but on the other hand, the water production rate measured by MAJIS is not produced by the nucleus, because from this production rate, in fact, we can determine that this water production is much larger than the nucleus can produce. In fact, the nucleus is too small to produce such high water production rate. So this shows that even based on the MAJIS data, 3I Atlas is an hyperactive comet with H2O molecules which are produced from subliming icy grains. And this, based on the radial distribution of MAJIS, these icy grains are very short-lived and release their water very close to the nucleus. What we see also on this graph is that the water production rate decreased steeply with increasing heliocentric distance, much more steeply than CO2 and CO. And this is easily explained by the fact that water is produced by icy grains, because the lifetime of icy grains at large distance is decreasing a lot. And so the icy grains at large distance are less efficient in producing water molecule. Then about CO2, so what we find is that the CO2 to H2O ratio is 10% near perihelion. And what we see is that the CO2 production rate is varying with heliocentric distance. And this has say something about the mechanism of production of CO2. It says that the CO2 outgassing is operating very near the surface or deep at some shallow subsurface reservoir. Otherwise, if CO2 would be outgassing from deep inside the nucleus, we would have expected a constant, almost constant CO2 production rate. So what we argue in our paper is that CO2 is the main activity driver of comet 3I at perihelion. It's not because you measure CO2 to H2O ratio with MAJIS of 10% that water is the main driver of the activity of this comet at its perihelion. First, because we have seen that water is produced from icy grains, and also because the radio data, so those acquired with SWVI, but also those acquired with ALMA or with the IRAM 30-meter telescope, they all show that the gas outflow velocity are about 2 times lower than what we measure in solar system comets. And an easy explanation to explain this low velocity is that the gas flow in the coma is driven by heavy species like H2, like CO2 and CO. So at perihelion, we believe that the activity was driven by CO2 and CO because CO is also the relative abundance of CO with respect to CO2 is about 1 at perihelion. So I see here, I show here it's a plot, so it's just a plot showing the relative production rate of in red CO2 over H2O, in green CO over H2O, and in blue of CO over CO2. And so we see that this ratio varied a lot with heliocentric distance. So here we can discuss, for example, on the CO over CO2 ratio. And so this combined measurement with MAJIS, but also with GWST and IRAM, etc. And so what you see here, for example, is that at large pre-perihelion, at large heliocentric distance, the CO to CO2 ratio was low, so the activity was driven by production by CO2 outgassing. When the comet was at perihelion, in fact, the activity was driven by CO and CO2 at about the same rate. But after perihelion, in fact, the CO2 activity was driven, the activity was driven more by CO than for CO2. And this, we can explain that by heat transport toward deep subsurface layers. So we can explain that by the fact that as the comet approached the sun, in fact, the subsurface layer was heated more and more and more, and the CO present in the deep internal layer could more and more sublimate. Another thing to say is that we can measure the C to O ratio, and this C over ratio is among the larger value measured in solar system comets. So this indicates that this comet was quite rich in hypervolatile species and formed in its planetary disk, likely at distances beyond the CO2 snowline and maybe CO snowline. So I have 2 other results to present. First, that with MAJIS, we measure the color of the dust. So this is interesting because it's a unique measurement of the dust color at perihelion. But in fact, the dust color was measured by many instruments at different distance from the sun. So we measure the red slope below 1.9 micron, which is consistent with the value measured by other techniques, by other instruments at different distance. And we measured only a slightly red slope at longer wavelengths above 0.9 micron, and this is also globally consistent with other measurements. So if you go to detail, we have slight differences, but there are also slight differences between other measurements from the grounds. So we can compare this color to the color, for example, of the dust in short period comets. So this is shown in green. This histogram in green. So we see that 3i is in average as the color which is in the average of measured in short period comet, while it is redder than in long period comet, but bluer than in TNO families. So I will stop there, but this red color, in fact, are attributed to organic material. There is no special extraordinary result for 3i. So finally, my last presentation, my last slide is that we have detected the 3.4 micron band. So this feature, which is in fact a characteristic of CH stretches, either in simple organic molecule or complex solid organics, in fact. In comet, usually in comet, in fact, this band is mainly due to the fluorescence emission of methanol and C2H6. But what is strange for the spectrum that we obtain for comet Atlas is that taking the methanol production rate, which was measured at the same time with the IRAM 30-meter telescope, in fact, we cannot explain the spectrum that we detect. We have some residual emission, and what is also very interesting is that we have residual peaks which coincide just with the expected signature of CH3 stretches, asymmetric and symmetric stretches, and CH2 asymmetric and CH2 symmetric stretches. And so this indicates if this observation is correct, because the signal to noise ratio is not very high, but this indicates the presence of abundant organics in the atmosphere and with aliphatic carbon chains. So what we note is that this extra residual emission is not seen in James Webb data taken at 2.4 and 3.3 astronomical unit. But there is a recent paper by Belyakov showing the detection of a 6.9 micron band from MIRI observations with the James Webb, and which could be due to organics. And maybe the two observations are connected. So I am stopping here saying that MAJIS has provided key and unique measurements for the understanding of the composition and activity process in Comet Atlas. Thanks.
We will go to our final talk for today, moving up the spectrum to the ultraviolet with Philippa Molyneux. Philippa is a lead scientist at the Southwest Research Institute in San Antonio, Texas, and she's the co-deputy PI, the PI cannot be here today, of UVS on Juice. Philippa, floor is yours.
Okay, so I just want to start by quickly acknowledging a few people. So Kurt Rutherford is the PI of the Juice-UVS instrument. He put together these slides, but unfortunately couldn't make it to present them in the end. Tommy Greathouse and I are the two deputy PIs, and Martin Versteeg is our operations and flight software lead. And lots of people within the team helped to plan and execute these observations. So thank you to all of those. So the ultraviolet spectral region is great for studying comets because lots of common atmospheric gases that you might expect to see in a comet coma, including things like hydrogen, oxygen, and carbon, have strong emissions in the ultraviolet. This is something that's been demonstrated by ultraviolet instruments in the past, including the ALICE spectrograph on ESA's Rosetta mission, the Lyman Alpha mapping project, on the Lunar Reconnaissance Orbiter, which is a NASA mission, and others. These two instruments that I've just mentioned are essentially earlier versions of Juice-UVS. They were built by the same team, and they have a very similar optical design. So when we started planning our observations with Juice-UVS, we looked back at what they had done to give us an idea of what we might expect once we perform these observations. And then one other thing to mention is that we also have a UVS instrument on Europa Clipper. So as shown in this diagram on the left here, Europa Clipper was also able to observe Atlas from a very different viewpoint than Juice-UVS, and I will briefly mention those observations just at the end of this talk. Okay, so here are some example Rosetta and LAMP observations of comets in UV. So I'll start with the image in the top right here. So if you look at this, it's a LAMP spectral image of comet sighting in spring. It's a fairly distant observation, and the x-axis along here tells you the wavelength of any photons that are detected, and then the y-axis tells you where in the field of view that photon came from, and the field of view is like a long, narrow slit. So in this image, we see oxygen that's coming from right around the comet, kind of near the middle of the field of view. We see this Lyman alpha line, which is a very bright hydrogen emission that fills the entire field of view because everywhere we look on the sky, there's hydrogen. There's also another feature called the Lyman alpha ghost, which is a detector artifact. It's a reflection of Lyman alpha within the instrument. I just want to point that out because it appears in all of the JUICE spectra. So that's what that is if you see that. So to extract a comet spectrum from this, we would sum over the rows that contain the comet. This is shown in the panels down below. This, as I said, is a distant observation, so the spectrum is fairly noisy, but it was good enough to make estimates of the water production rate from the hydrogen and oxygen lines, and also to put upper limits on various other species in the comet's coma. So that was kind of our lower expectation going into the JUICE observations. We thought we'd probably see something similar to this at least. And then if we were very lucky and the comet was very bright in the UV, then maybe we'd see some additional emissions. So this is an example from Rosetta Alice. Rosetta was orbiting comet 67P, so very close, was able to detect a lot more. There are things like carbon and sulfur in here, and some additional hydrogen lines as well that we may have detected if we got lucky. All right, so I'm going to come back to this again in a minute, but this is just sort of a preview of what we got with JUICE. So again, you can see we saw the bright oxygen line that was detected by LAMP. We saw hydrogen, Lyman alpha filling the slit. We were also able to detect a few additional features from hydrogen, Lyman beta, and some carbon emissions. In this particular observation, there was a star in the slit as well, which we see down here. And just in case I forget to mention this later, I want to point out it looks like there's kind of a hole in Lyman alpha here. That's not a real spatial effect here. This is an instrumental issue where the comet was so bright at Lyman alpha that the detector electronics were not able to kind of process every photon correctly. So there's some extra calibration that we need to do to just kind of correct for that and get the correct flux. So please ignore that in future images that I show. And again, we see this kind of artificial artifact, this reflection within the instrument here. So stepping back for a moment, I'll just kind of briefly summarize the observations that we did. So this table contains a lot of data and I don't want you to read it all, but I'll just point out a few things. So we observed on 7 occasions between the 2nd of November and the 25th. The first 6 occasions, we were just staring at the comet. So Juice-UVS does not have a scan mirror like MAJIS does, so we can only perform a scan if the spacecraft moves for us. So we didn't do that in these first 6 observations, but on the 25th of November, we were able to make the spacecraft slew and scan across the comet for us and get some spatial information there. The other thing that I'll just mention is this HIST-PIX column. So we have 2 modes of collecting data with UVS. One is called pixel list mode, and in that case, we collect a list of X, so spectral coordinates, and Y, spatial coordinates, for every photon that hits our detector. And then we use them to create the spectral image on the ground. In histogram mode, the instrument bins up that data on board into spectral and spatial bins. So what we receive from the spacecraft already kind of looks like that image that I showed from LRO LAMP with it's already kind of a 2D array. So just as I mentioned, histogram and pixel mode later, they contain basically the same information, but they're just collected in a slightly different way. Okay, and then this slide just shows why we were able to do the scan on the last day. So on the 25th of November, the comet just happened to kind of naturally pass just above our field of view. So the spacecraft only had to slew a little bit, just perform a roll for us to scan over that comet. Whereas on other days, it would have required a lot of off-pointing and it just wasn't possible. Okay, so now we can start digging into the data a bit more. This is the same image that I showed a few slides ago. It's the sum of the 3 star observations that we performed in pixelless mode. And so I've already kind of pointed out the main spectral features here. To extract a spectrum from this, we can sum over these central rows that contain the comet, and then you can see this. This is an uncalibrated spectrum in black. And then we're also showing kind of the background levels in blue here. This is just a few rows near the top of the slit. So you can see that these emissions are definitely coming from the comet and not just present in space. So to convert that into a calibrated spectrum, then we have to correct for the effective area or sensitivity of the detector, which changes with wavelength and also with position along the slit. And so this summarizes those calibrated spectra that we get after doing that correction. We're cropping this to a slightly smaller wavelength range here, so starting at 110 nanometers. That's just because we're still working on the calibration of the short wavelengths, so they would look crazy if I showed them here. And this is in intensity units, Rayleighs per nanometer, Rayleighs defined down here. So what we see here is this kind of trend in increasing brightness towards the longer wavelengths. That is sunlight. That's the shape of the solar spectrum. And so we're seeing sunlight being scattered maybe by ice grains or something near the comet. And then we still see these, the carbon lines here and the oxygen line at 130.4 nanometers. The first 4 observations, so the 2nd and 5th of November in pixelless mode and the 3rd and 6th in histogram, all of those spectra look very similar. And then as we started to move further away from the comet and the more distant observations on the 12th and the 19th, the comet looks dimmer. That makes sense because we're further away from the comet's further away from the sun. But one thing that's kind of interesting to note is that the oxygen emissions did appear to kind of drop before the carbon ones. That kind of looks clearer if you take the ratio of the 2nd and 3rd histograms here. You can see the oxygen emission was more than a factor of 5 brighter on the 6th than on the 19th, whereas everything else was sort of changing by about a factor of 2. All right, but just because we saw less oxygen emission, that doesn't mean that less oxygen was present. So the emissions that we see, they're mainly due to oxygen absorbing and then re-emitting sunlight, and it can only do that at very specific wavelengths. So if you look at the solar spectrum around this wavelength of 130.4 nanometers, you see, so it's actually a triplet emission, 3 very narrow lines, and there's very little solar continuum near these lines. So as we were observing the comet over this time period, it was moving further away from the sun, and it's the component of its velocity that was in that direction along the line of sight to the sun was increasing. So that meant that there was a Doppler shift in the sunlight that reached the comet. So then if I'm just going to zoom in on one of these lines in the oxygen triplet to make this a bit clearer, but this kind of shows how the magnitude of that Doppler shift was changing over time for these last 3 observations. So from the 6th, the 12th, and the 19th of November. So yeah, we think that probably a lot of the decrease in oxygen that we were seeing is due to this move away from that peak in the solar spectrum. So there was just kind of less light that the oxygen was able to scatter. And this is an effect that we kind of need to work on a bit more and correct for before we're able to determine the column densities of all the gases that we're seeing in our observations. So that's kind of ongoing work. And just note that this The reason we see this more at oxygen than at carbon is because the carbon lines in the solar spectrum are broader. There's more continuum, so there's still more light that can be scattered at the wavelength when it reaches the comet. All right, so as well as spectral information, we get spatial information by looking at the distribution of emissions along our slit. Again, I'm going to ignore Lyman alpha, even though it's the brightest line, because of this kind of weird effect that we haven't fully corrected for yet. So if we look at a few of the different emission lines, we can see how broad they appeared, like what was the size of that central emitting region that we were looking at. So this is an example from the 2nd of November. And we're looking at the Lyman beta line, the oxygen 130.4 nanometer line, and then one of the carbon lines over here. We can do a fit with a Lorentzian distribution and then find the width of that. And that tells us kind of this size of the emitting region. So we got sizes that ranged from around 500,000 kilometers for Lyman beta and up to just over 800,000 for the carbon emissions. But we can't yet say that there's any difference in the distribution of these different gases, because we also need to consider that the resolution of our instrument varies with wavelength. So our resolution is best around the hydrogen Lyman beta wavelength, which is this smallest distribution, and it's worse at carbon. So that may explain why we're seeing these different sizes here. We still have another step to go to correct for that and see if there is any difference in the distribution of the gases. All right, and then moving on to the scan image, by the 25th of November, unfortunately, the individual emission lines were too faint for us to really detect any specific, well, especially the carbon and oxygen lines. We can map those individually, and you can also see that the brightest things really in our slit are stars. This is a spectral image that we've just taken all of the data over the full scan period and mapped that to the spectral and spatial period pixels, and yeah, all we really see is stars and Lyman alpha. But when we filter out this kind of messy Lyman alpha region and we sum up all the photons and we map them to the sky, then we were able to see this kind of diffuse region in the center of our image, right where we expected the comet to be. And then we can try a few tricks to kind of confirm that that's the comet and take out some of the stars. So the first thing that we did was we looked at a very narrower wavelength region. So most stars are not bright at wavelengths shorter than about 115 nanometers because that light is absorbed by the interstellar medium before it reaches us. So we filtered to those shorter wavelengths, and then again, we still have a few stars left, but we are still seeing this diffuse region right where we expect the comet to be. The other thing that we can look at is the Lyman alpha ghost feature, so that instrumental effect, the reflection inside the instrument. This is essentially a fainter and inverted map of the hydrogen Lyman alpha. So again, it's concentrated right where we expected to see the comet. So we're still working on kind of cleaning up these images and getting a more quantifiable result from them, but we found the comet, we saw it, we were able to image it, so that was great. And then finally, one other thing that we've tried doing was doing more of a spatial filtering, so getting rid of the stars and just playing with the scaling a little bit. And again, you can definitely see that there's a concentration in emissions in the center of the image where we expected to see the comet there. All right, and then I finish off with a quick comparison to our other instrument, Europa-UVS. So we were lucky enough and fortunate enough, and thank you to the Juice team for making this happen. We were able to observe simultaneously with both Europa-UVS and Juice-UVS on the 6th of November. They were looking at the comet from a very different point of view. So Juice was sort of on the day side of the comet, looking at the daylit atmosphere, and then Europa Clipper was more on the night side, looking back. And so the Juice image that I'm showing here is a histogram image. The previous ones I've shown have all been pixelless, so you can see there's a slight difference. That's because we can change the binning that we use, the spectral binning. So we've used finer sampling around Lyman alpha just to avoid saturating the image there, and then we've used broader, bigger bins outside of that region because these are fainter emissions. So that's why that looks different. But as in the previous examples I've shown, we were able to see oxygen, the Lyman beta hydrogen emission here, and the carbon lines. Europa-UVS saw a lot of scattered light that's filling the slit. But they were also able to see emissions from hydrogen and oxygen. You can just about make out the kind of central region here where the comet was centered within their slit. And then this is a map that we made from the Europa-UVS data. It's false color RGB map. So the blue is the hydrogen being concentrated right on the comet there. We were also able to observe with LRO LAMP. Kurt is also the PI of LAMP, so he made that happen too. I don't have that data to show yet, but that's something you can kind of look out for in future. So yes, 3 of our UVS family of instruments were able to observe, which is great. That's everything we have. Still some work to do to get some quantifiable numbers out of this, but we're very excited and we're very happy to have these successful observations.
Great, thank you so much, Pippa. It's amazing data. Must be the first time that Juice and Europa Clipper are observing the same thing at the same time, I guess.
I think so, yeah.
Wow, it's amazing. Okay, we have a few questions already lined up. I see 3 questions in the Q&A, and there's some comments here in the chat. Callum, would you like to go with the first question?
Yeah, thanks, Martin, and thanks everybody for your questions. Our first question comes from the Q&A with Martin, who asks, what H2O author power ratio was assumed for the SWI-DH analysis? With JWST spectroscopy of multiple H2O lines, we found an author power ratio of about 2.7. So this could affect the fit of observed ortho and para lines. Who will field this?
Yeah, I would say within the error bars, we at the moment we could also say 2.7, but on the other hand, the error bars are relatively large, so we assumed in the fundamental modeling 3.
Thank you.
Dominique, you have something to say? It's a big specialist on this area.
For interpreting the MAJIS data, we assume 3, but okay. I don't know. I'm not sure that it will change a lot the results.
Right. But Paul, so from the SWI data, you have 2 lines. You showed 2 lines, right? You showed line from ortho and para water. Correct?
Correct, yeah.
So from those lines, can you not determine?
Yeah. You can determine in principle, but you saw the lines are also relatively noisy, right? And 65 million kilometer to 64 million kilometer distance, 25 minutes integration time. I would say we cannot say that it's not 2.7.
Right. Okay.
But it's the same ballpark. So it's not a measurement where we really can very precisely measure the ortho to para ratio, let's say with 5% or 2% error. Okay. So I would say 2.7 is very well possible, but 3 also concerning our measurements.
Okay, thanks. Okay, then the next question is by Nicolas Atri. A question to Paul. Water flux was higher anti-solar than subsolar, implying extended sources in the coma. But did you also show the anti-solar velocity was higher too, I think? Does this imply superheating of the grains in the coma?
Oh, no idea. Cannot be excluded, I would say, but superheating, we frankly speaking, we didn't discuss it here. So you mean particles were small enough that superheating appeared, and so due to that, the gas was accelerated. I guess that's the idea behind this. No, I cannot answer this question. I would say possible, but so not really a constraint in the measurements and in the model.
Maybe I can answer.
Sure, Dominique.
Because in fact, in the model which are used to interpret the SWI observations, we do not take into account that the water molecule could be produced by grains having a velocity of something like 200 meters per second, accelerated. You see, so for the moment, the velocity that you measure in the night side is not directly maybe the velocity of the molecule. You understand? Because in fact the molecules are produced by grains which have some velocity in the antisolar direction. But in the model, we do not, the model are too simple, even if they are complex for the radiative transfer, to take into account the kinematics of the production of the water molecule. Okay.
Okay, I hope that answers the questions, Nicolas.
One comment to this also, maybe. So I think in the plot I showed, we see that the main production of the water vapor by the grains is happening relatively far out, where the density is so small that any heating effects of the grain wouldn't probably have some kind of effect on the speed. Because there are no collisions. That could happen only very, very near to the nucleus, I think. And so therefore, whatever happens, I mean, we don't have it in the model, as Dominique says, but so at the moment, I cannot imagine how this could work.
Thank you both. Our next question comes from Rekka in the Q&A. Rekka asks, taken together, the extreme DH enrichment, the evidence for hyperactivity, and the inferred formation towards the CO2 snowline, do these observations point towards a formation environment that is fundamentally different from the outer solar system? Or could 3I Atlas still be considered for an extreme analog of our own Oort cloud comets?
I think we need 1 hour to discuss about that.
We can have another webinar on this one question.
Part 3.
No, but there have been a lot of observations of 3I Atlas, and some of the observations, I am referring to the observations, the measurement of the isotopic ratio, but not only the overage, but also the carbon 12 to 13, etc. They show that the environment where this comet formed was totally different from the environment where the solar system comets form. For example, there is a very anomalous carbon 12 to carbon 13 ratio, which is much higher than the values that we found in the solar system and the solar neighborhood. Also, the N14 to F15 ratio is different. The D overage is different, and so these comets, it form in a completely different environment, and they are even constrained on when this comet formed. This comet formed maybe something like 9 gigayears ago. So
you couldn't even try to look in the sky and see where do we find similar abundances in molecular clouds, because it might have been gone by now.
No, we do not find molecular cloud with so high D overage ratio. We do not find a region with so high carbon 12 to carbon 13, etc. There are papers which have been recently published in Nature by Martin Cordiner, Cyril Opitom. You can look at them, and but the MAJIS, not the MAJIS, but the Juice observation do not provide answer about that. It's, I think, about the origin of the comet.
Okay, next question is by Marshall, who asks, did anyone find any indication of PAS in the 3I Atlas data? Polyaromatic hydrogen. Is there any indication of those?
in the MAJIS data, but even in the data from James Webb, we do not see a signature at 3.29 microns, which are where you expect signature from cyclic, I would say, benzenic association, you see, of pH. So we cannot say.
Okay, I hope that answers the question. Go first.
We have two questions in the Q&A next from Masoom. The first reads, since Juice caught 3I Atlas at its most active phase during perihelion, what do the observed jet structures and outgassing behaviors reveal about its surface about its subsurface structure? Does the data suggest this interstellar visitor has retained its pristine primordial material, or has it been heavily processed by its journey across deep space?
Yeah. There have been some estimation of the erosion, the erosion of the nucleus. So there are papers in the literature about that. So I do not remember the question exactly, but in fact, the material we are seeing was deep in the subsurface. What was the question? I do not.
Yes, the question was, since Juice caught 3I Atlas at its most active phase during perihelion, what do the observed jet structures and outgassing behaviors reveal about its subsurface structure? Does the data suggest this interstellar visitor has retained its pristine primordial material, or has it been heavily processed by its journey across deep space?
Okay. I think we cannot say that it has been. I think it's not easy to answer to this question. What we see is that the comet is rich in volatile like CO and CO2, so it did not lose its volatile.
The question is what should have caused the processing cosmic radiation? Because in principle, we can imagine that it didn't see some star or something like that and wasn't warmed up for billions of years. So who knows that? So therefore, I can only imagine processing could take place by cosmic radiation.
But that would affect only the surface.
I mean, the processing of the surface. So usually it interacts with electromagnetic radiation and maybe dust or so, even in the interstellar medium, right? But for me, it doesn't look like it was heavily processed. But anyway, it's pristine, probably the most pristine object we have seen.
Thank you both.
Okay, another question by Masoom. Are the processed MAJIS level 2 calibrated spectral radiance or derived level 3? Map projected columns. Data products are those data products for 3I Atlas observations already available to the public at the ESA PSA? Or are they currently undergoing proprietary team validation? So basically, can we download the data now and start working on it on our sites? Claire, you want to say something about that?
Well, I don't know if Dominique wants to comment, but at the moment they are not yet available to the public in the PSA. So they will be later on during cruise. But at the moment, no, it's still under a proprietary period, yes.
And I guess that goes for all the instruments, or
yes, yeah, absolutely, yeah.
I have nothing to add.
So a little bit more patience, I guess, yes. Okay, you want to take this one? There's one more question I see in the Q&A box.
Oh, yes, thank you, Martin.
And
our final question is from Martin, who asks, for Dominique, it seems that H2O was probably the dominant volatile in 3I Atlas. Do you have any preferred physical explanation for why the nuclear sublimation was dominated by CO2 and not H2O?
I don't know. Okay, it's I don't know. It's an hyperactive comet, so in the category, I don't know. I would have to think more about that. I would say that this comet is quite is very rich in CO2 and volatile, and maybe the grains are very ice rich, so that the outgassing of the comet is dominating rather by the most volatile species rather than the more
Tricky
difficult question.
tricky question.
Thank you.
Thank you so much. And I think we can consider the session a wrap. Thank you so much, everyone, for being here. Thank you so much to our three speakers, Claire, Olivier. Wonderful. So next presentation for Juice will be after the summer. And but our next webinar will be next week in exactly 7 days, in next Tuesday. And we'll talk about the night sky and how we can keep it dark.
Fantastic. Thank you, everybody. Have a good evening and rest of your day, and we will see you next week.
Absolutely. Thank you, everybody.
Thank
Goodbye.
you.
Goodbye.
Bye-bye.
Bye.